Welcome back. This is the second video on confidence intervals, and we're going to focus in this video on confidence intervals for the population mean. And so we're going to talk about things that you need to think about before you compute a confidence interval. We're going to look under the hood a little bit and try to understand how confidence intervals work. And in doing so, it'll make sense of some terms like confidence, for example. And then we're going to actually use StatCrunch to make the confidence interval for a couple of examples and see how that works. And finally, we're going to take a closer look at the margin of error. And we want to try to understand what factors affect it and how. But before we start, you probably want to pause the video if you haven't done this already and go ahead and download this data set, which is in this module, and go ahead and import that into StatCrunch. Okay, so what do we need to know before we begin to get into computing a confidence interval? Three things primarily. The first and the most important thing is we have to check and make sure that the two assumptions we need to satisfy in order to use the central limit theorem for population means is satisfied. And the reason why is we're going to see in the next section that the theoretical basis, the reason why confidence intervals work, in very much the same way as we saw for hypothesis tests, is the central limit theorem. So it's both a theory underlying hypothesis tests and confidence intervals. And so the assumptions that we need to satisfy are exactly the same as when we had the hypothesis tests. Nothing new there. And one thing that in general we need to know, but in this class we're not going to have to worry about, is generally we need to make sure that we know what standard deviation is being used. So there's a population standard deviation and a sample standard deviation. In this course, we're going to only work with the sample standard deviation. And the reason why is if you don't know what the population mean is, it's a little naive to think that you know the population standard deviation, since that's a measure of the average distance from the population mean, which you don't know. You're trying to estimate. The third thing, and this is a more practical matter, when you're using StatCrunch, you have to think about whether or not you're working with an actual data set or are you given the summary statistics for a data set. And we're going to talk about how that comes into play. But these are the three things that we want to get a handle on before we begin to do any sort of computations. We want to get a little bit of an understanding of the theory for confidence intervals. And even though we're not going to compute them by hand, understanding where they come from really gives you a deeper appreciation and a much better understanding of this section. We're going to start off talking about a 95% confidence interval for the population mean. And let me set up what I mean by that using a concrete example. So we start off with some population and a quantitative variable of interest. And I'm going to use what we had in the discussion boards. One of the variables that you could have collected data on was hours of sleep you get in one day. And so there's the population of all the hours of sleep, say, a person might get. We go ahead, we take a random sample, and we want to compute the sample mean. And now what we want to do is we want to put a little error bar around our sample mean. The book uses capital E as the abbreviation for margin of error. MOE is another common abbreviation, and I'll use them both with equal frequency. Probably I'll use MOE a little bit more, but when you're doing the homework, you'll see capital E instead, usually. And here's what we want that margin of error to do, and this is important, so you want to listen carefully. We want to find some value for this error bar such that when I put it around the sample means for 95% of the samples, this confidence interval, so this red bar here, is going to contain the population mean. That's our goal. So our question is, how do we find this margin of error so that for 95% of the samples, this red bar, this confidence interval, will contain the true value for the population mean? And we're going to get into this. So, first of all, let's suppose that the conditions to use the central limit theorem are satisfied. And let's suppose we knew the population, standard deviation, and mean. We don't, but just for the purposes of argument, okay, just for the sake of our argument. What do we know about the distribution of the sample means for a given sample size? Well, again, the central limit theorem tells us what the distribution, that is, what the population of sample means that are drawn from a population where we have a standard deviation of sigma and a mean of mu. It says the sample means have a normal distribution, they're centered at the population mean, and their standard deviation is the standard deviation of our variable divided by the square root of the sample size. And we're going to use this notation as a useful way to remember this is the standard deviation of our sample means, not the standard deviation of our variable. Again, we want to bear in mind that the individual values, that is the variable values, and the sample estimators have different distributions. That was the lesson of the sampling distribution that we talked about in an earlier module. Now we're going to use this information to see how to construct this 95% confidence interval. So what I want you to do is I want you to make a drawing. I want you to sketch out a normal distribution for the sample means with 3 standard deviations on each side. Okay? And now I want you to make a confidence interval whose margin of error is twice the standard deviation. So this is this red bar. Notice each of these is 1 standard deviation, right? So this is 2 standard deviations, 2 standard deviations. And now what I want you to do is pick a point anywhere on the number line. So I'm just going to randomly pick some sample, and my sample mean would be here. And now I want you to center this confidence interval at the blue dot, at the point that was chosen. Okay. So this is the confidence interval that has a margin of error of 2 standard deviations. And here's what we want to note. Your confidence interval will contain the population mean if the sample mean you chose is within 2 standard deviations of the population mean. So for any x bar chosen in this region right here, the confidence interval will contain the population mean. So let's put this all together. So the empirical rule tells us 95% of the sample means will be within 2 standard deviations of the population mean. And so we can conclude that from that for 95% of the sample means, if we use a margin of error of 2 standard deviations, our confidence interval will contain the parameter value. And that's what we want a confidence interval to do, ideally. So congratulations, you just made a 95% confidence interval for the population mean. You just found an error bar, that is a margin of error, of 2 standard deviations, and you showed that for 95% of the samples, the sample means, when I use that 2 standard deviation error bar, will contain the population mean. And that's what a 95% confidence interval means. Now, we got lucky, and that 95% just happens to be a nice even number of standard deviations from the empirical rule. But what if we wanted to work with a different percentage. Maybe say 90% instead of 95%. So now we have to go back and review a few facts about normal distributions. So we recall that when we're talking about a standard normal distribution, we generally use the letter Z. And this is a special type of normal distribution, a normal distribution that has a mean of 1 and a standard deviation of 0. And the second thing we want to recall is that if any variable, which I'll just call X, has a normal distribution, its Z-scores have a standard normal distribution. That's important. So now a little bit of notation here, okay? So if I want to find the Z-score that's in the pth percentile, in other words, the probability of getting a random value less than Z is equal to P, we're going to use the following notation, Z sub P. And we actually used this before when we were talking about measures of relative standing and how to compute the percentile from a data set using StatCrunch. And so if, for example, we were talking about a probability of 2.5%, we know from the empirical rule that the Z-score that has 2.5% in its left tail is -2. Okay. Because we know there's 95% in the middle, 5% in each tail, and so there's 2.5% in each tail. All right, now that we have this notation down, we can start to get into the nuts and bolts of how these confidence intervals are constructed. So if we have a normal distribution, let's ask the question, what Z-scores contain the middle 80% of the values? You should remember that the homeworks talk a lot about the symmetric interval that contains 80% of the values. This is what they're talking about. Let's do a little sketch. So here's how the distribution of Z-scores would look for a standard normal distribution. And we don't know where there are, but you can use the empirical rule to figure out it's between 1 and 2 standard deviations. So I'm just going to kind of choose 2 values between there, the same distance away. And we want to choose those 2 distances equidistant from 0 such that they contain 80% of the area. And now we play this game. All the areas have to add up to 100%. So if the whole area under the curve is 100% and this middle portion is 80%, these 2 portions, these 2 tails have to add up to 20%. And I cold-bloodedly chose those values so that this was symmetric. So these are each half of 20% or 10%. That's what middle 80% means. It means that the values that bracket that 80% are symmetrically located about the mean. And I can compute those scores. This first one is just the Z-score for the 10th percentile. If you put this into StatCrunch, you'll find out that it's roughly minus 1.28. And this upper value is the Z-score for the 90th percentile. And again, due to symmetry, they're the same value, they just differ in sign. But that doesn't help us. Okay, we don't want to know the Z-scores that bracket the middle 80%. I want to know the values of X bar, the sample mean, that are going to bracket the middle 80%. So if I translate this picture to sample means, 0 becomes mu. And -1 becomes mu minus 1 standard deviation, and so on. Remember, a Z-score of -2 tells me how many standard deviations I am below the mean. So this is the value that's 2 standard deviations below the mean. And the standard deviation for X bar is denoted by sigma sub X bar. And I know what these values are. The way that I translate Z-scores to data values is I multiply the Z-score by the standard deviation and I add mu. So this X bar is mu minus 1.28 times sigma x bar. And the upper one is plus. So now I have the margin of error for an 80% confidence interval. Notice that if I subtract mu from both sides, this distance that I am away from mu is 1.28 times the standard deviation of x bar, or z sub 10 times sigma x bar. So we've computed now the margin of error for a situation where this percentage is not a nice number we can use the empirical rule for. Because I computed this number using StatCrunch. I didn't have an empirical rule for this. So how would this work in general? Okay, so when we say 95% confidence interval, this 95% has a special name. It's called the confidence level. It's the level of confidence we have. And we're going to come back and interpret what that means. But for right now, just know the term. And just like in hypothesis testing, we had alpha of 1%, 5%, and 10%. Usually for confidence levels, we have values of 90, 95, 98, and 99. You may notice that these are the complements of, with the exception of 98, these are the complements, 90, 95, and 99, for alpha in the hypothesis test. And we're going to see that's not an accident. Next week, we're going to talk about the fact that there's a relationship, actually, between confidence intervals and hypothesis tests, which is really important. But for right now, just know these are the values that we're typically going to use. When there's no value given, usually 95% is used by default. So when you listen on the news and they give the confidence interval for not the population mean, but a population percentage of a candidate, they'll say what percentage of people are going to vote for Biden, 47% plus or minus 2%. That's a confidence interval, 47 plus or minus, meaning if they think the true value is between 45 and 49%. And that confidence interval is a 95% confidence interval. That's kind of the standard or the default confidence level we're going to use. Now, from our previous slide, what we saw was that the confidence level is the probability in that symmetric middle area. That 95% confidence interval that told us to find the z-scores that contain the middle 95% of the values. And so the tails contained, the area in the tail was 1 minus the area in the middle portion divided by 2. And so this told us that the z-scores containing this middle area are z sub 1 minus confidence quantity divided by 2 from 0. These are our z-scores that bracket the middle confidence level area for a standard normal distribution. And so what that means, if we translate now from data values to z-scores, notice all I'm going to do is multiply the z-score by the standard deviation. And this is giving me the margin of error. So this tells me what my margin of error is. And if you go back and work those two examples, this will maybe make a little more sense. This is a little esoteric because we're using a lot of notation initially. But that's all that's going on. Now, just like the confidence level has a special name, this score, this z-score also has a special name. It's called the critical value for reasons that I won't go into. So there's a little bit of notation and terminology you have to know. Confidence level and critical value. And so now we see how the margin of error is put together. And this is important. If you understand this formula, you understand what's going on. It says the margin of error is equal to the number of standard deviations we have to go away from the mean so that we have the confidence level area in the middle times the standard deviation of the sample mean. So it's the number of standard deviations times the standard deviation. And those number of standard deviations are chosen so that they contain confidence level area in the middle portion of the distribution. This is a very fundamental sort of formula and idea in statistics. Okay. Now, here's the catch. We said at the very beginning we normally don't know the population standard deviation. So what do? Well, we do the obvious common sense thing. If I don't know a population value, what would I use in place of it when I have a sample? I'd use the sample estimate. So instead of using the population standard deviation, I'm going to use the sample standard deviation from my sample. However, this changes our formula a little bit. When we shift from using the population to the sample standard deviation, we can no longer use z-scores. So the critical values don't come from the standard normal distribution. And instead of a z-score, we use something called a t-score. And these t-scores don't come from the standard normal distribution, but a distribution that looks very much like it called the t-distribution. So it also has a mean of 0, but it's a little fatter than the standard normal. It's a little bit wider, okay? And this is called the t-distribution. And I'm not going to get into this a lot, but what you want to know is that when we're working with these critical scores in the t-distribution, sometimes you'll see two subscripts associated with them. The one is not a surprise. It's the same as the z-score. We have the probability in the lower tail. That's that probability p. The other one, the z-score, does not have. And this df stands for degrees of freedom. And I don't want to go into what degrees of freedom mean. All we need to know is that it's one less than the sample size. So if I wanted to find the degrees of freedom, I would just take the sample size and subtract 1. And you'll see it on the output. We're generally not going to use that, but just something to help you kind of get your bearings and understand what you're looking at. So now all we do is we swap out the z-score for the t-score and this sample standard deviation for the population standard deviation. And let me go back and compare these two formulas just for a moment. Okay. So this is what we had before. And this is what we have now when we don't have the sample standard deviation. Okay. So what do? We swap out the z-score for a t-score. And this quantity right here, which I'm going to write over because I really want to emphasize this. I've noticed that people are really having trouble understanding the standard deviation for the estimates. So this would be sigma divided by the square root of n. And in lieu of that, we swap out the sample standard deviation, S, for sigma. Okay. So when I come down here, I'm going to swap out sigma for S. Okay? And that's all we change. Now it's important to understand something, okay? And this is not so obvious, and I'm not going to belabor this, but it's easy to get confused, okay? Is that these things are approximations now, okay? And I'm not going to use the word approximation. So I'm going to talk about standard deviation of the sampling mean, which technically is this. Okay, this is the standard error, the actual. This is going to be our estimate. And so I'm not going to use the word approximate, but it's important to understand that this is not the exact value. This is an approximation. The theory still holds up. It still works. But again, these quantities are not exactly what we say they are. There are approximations. Okay. So let's go ahead and move on and now see how to actually use this. So what do we need here? If you think about it, we need a couple of things. We need our sample standard deviation, right? If you go back to this formula, I need the sample size, I need the confidence interval, the confidence level, and I'm going to have to put the margin of error around X bar. So I also need to know the sample mean. So if we were doing this by hand, we'd compute the margin of error. We'd use the confidence level and the sample size to find the critical value. And we'd compute the standard deviation of X bar, again, the approximate standard deviation. And we would compute the margin of error. We would just multiply them, that's all. Okay? And then all we would do is we would just take the margin of error and add it and subtract it from our sample mean. That's all we're going to do. Okay? And that's going to give us the upper and lower endpoints, right? And that's how we get our confidence interval. This is where it comes from. Now, we're not going to do these computations by hand, but again, if you can understand lines A, B, and C, if you really understand where they come from, you'll have a good idea of what's going on, and it will make it a lot easier to understand what we're doing, and it'll make sense. Okay, so let's see how to use StatCrunch now to actually compute these confidence intervals. So you have this data set downloaded and imported into StatCrunch. The context, what you're looking at in that data set is the ages that are from a survey of 25 randomly selected customers. And we want to compute the 98% confidence interval for the mean age. We're going to assume all the conditions are met. Now, age does not have a normal distribution. We've talked about this. Age is actually right skewed. However, sometimes when you're looking at ages in certain subpopulations, like people who go to a store, like, what are the ages of people who go to a boutique? Okay? Those are going to be younger people, a very small subpopulation, and very often they are normally distributed. But we're going to assume, even though we only have 30 customers, they are randomly selected, so our random sample conditions met, but our 30 sample size conditions not met, so we're going to assume that these ages are normally distributed. We want to find out what is the critical value and what is the margin of error also. So here's how we do this in StatCrunch. We go to stat, tstat, one sample with data. And then we're going to choose the variable that we want to compute the confidence interval for and enter the confidence level. And then finally, when we hit compute, we get our output. And so I'm going to do this. I'm going to work alongside of you here. So here we go. I already have the data set loaded. Thought I did. I thought I did, but I guess I don't. Okay, so let's go ahead and load it from a file on my computer. And there we are. Oh, I have it open, so I need to close it. Okay. And again, using good practice, we should look at the data values, make sure they make sense. There are no outliers, right? So let's just do that. It's always a good idea to kind of use good data practices here. So I'm going to go ahead and sort them. Notice that StatCrunch does something weird. It always puts the first value up here. And I'm going to have to start creating data sets where that's not actually happening. So do me a favor. Put 40 down here and put age up here. When StatCrunch imports a data set, it assumes you have headers. And I need to do that in the future. but it's not a big deal. It's just changing one value. Okay, and so I'm going to go ahead and sort on age. I look at this. There's a person 12 years old. Nothing strange about that. No weird values. 48. Those are all perfectly legitimate. So here we go. Stat, t-stat. The reason why we're using t-stats is because we're using the t-distribution. We don't have the population. We only have the sample standard deviation. So when we're working with samples and sample standard deviations, we use t-statistics. We only have one sample. We're going to talk a few modules down the road about doing 2 samples, but we're not going to deal with that right now. And we have a data set. So that's where you want to be. Okay, click on that. Click on my age. Make sure that you click confidence level. Don't click hypothesis test, okay? And we had 98%. So that's something important to do. And I'm not going to do anything down here. There's a lot of extra stuff that if you wanted to do, you could do, but we're not going to do that. Excuse me. And now we have our confidence interval right here. So this is our lower limit and our upper limit. And again, we're talking about age. So, we're not going to be having too many decimal places, right? Nobody says they're 28.395 years old. At least nobody that I know. And those are our 2 values. Okay. So if we round those off to the nearest decimal place, we're going to get 28.3 and 37.4. Okay? And the way that we say this, we're going to kind of wimp out a little bit, and we're going to use what the book uses for describing a confidence interval. But in the next module, we're going to learn how to do it precisely. It turns out that understanding what confidence intervals actually mean is something that is very tricky. And I'll tell you this very briefly. They gave a survey to people who actually do statistics in research settings, and it turned out that some really large number of percentage of people did not understand actually what a confidence interval meant, believe it or not. And so we're going to be kind of picky about this, and in the second section, we're going to talk about what it means. But for right now, all we're going to say is that we're 98% confident that the true average age of customers is between 28.3 and 37.4. And in the next module, we're going to talk about what that 98% confidence actually means. Okay. So now you know how to construct a confidence interval using data. Good. Again, our margin of error, we think about it, it's that error bar, right, around our sample mean. It's saying I know the population mean is most likely not the sample mean, so I'm going to put this little error bar, and I think the true population mean is in there. So if we want to find the margin of error, the first thing you can realize is that it's 1/2 the length of the total interval. And if we put in our values, we'd find out that's 4.574. The other method is I can realize that it's this distance from the sample mean to either endpoint. Again, taking the absolute value, right? I'm looking at distance, and I'll get the same value, of course. It's the same thing, same quantity. So let's go ahead for our reading quiz. What I want you to do is I want you to take those hours of sleep from that random sample that we introduced a long time ago, and I want you to go ahead and enter these numbers on the second line in StatCrunch in one column. And I want you to compute a 90% confidence interval for the population mean, just like we did with the data set for the ages, and figure out what is the critical value, what is the margin of error, and what is the confidence interval. So you can go ahead and answer those reading quiz questions now. Okay, so very often we're not given a data set, and we're going to be given summary statistics. And this is an example. This is a problem, say, from the book. A random sample of the price of gasoline from 40 gas stations in a region gives the statistics below. The sample mean is $4.49. S is the sample standard deviation. That's 26 cents. And they want us to find a 95% confidence interval for the mean price of regular gasoline in that region. First, always make sure that the assumptions are satisfied. So is it random? Yes, they tell it's a random sample. Is the sample size greater than 30? Yes. We have the go ahead. And the gas prices are probably normally distributed. And again, it goes back to the fact that, and this is kind of important, even though we're not going to be tested on this in the course, to get a sense of what's going on with the data. We know that usually financial data is right skewed. Okay, just like the ages were right skewed. However, again, when you're looking at a subpopulation, a small enough subpopulation, like in a certain region, it's not that uncommon for the values in a region, not a large population, but a smaller region, to actually have a normal distribution, or at least be somewhat symmetric. Okay? And when you think about it, it kind of makes sense. You know, most people in that region can afford a certain price. So most of the values are going to be bunched up, and there'll be a few places that can offer really cheap gas, like Murphy's, right, that has cheap gas, and a few places that have really high-end gas, okay? Okay, so the assumptions are satisfied. What values do we need? Well, let's see. So now we'll go back into StatCrunch, but now instead of with data, we're going to hit with summary. Okay, that's going to be the difference here, okay? And now what you're going to do is you're going to enter the summary statistics. The sample mean, the sample standard deviation, the sample size. Okay, those are the main quantities that we want to compute from the sample. And finally, our confidence level. And again, we're going to get our lower limit and upper limit. That's the lower and the upper endpoints. And we're going to see that we get these values. So let's just make sure this isn't a figment of my crazed imagination. Okay, so I'll just open up a new table here. You don't have to, but I'm going to. Stat, T-stat, one sample with summary. And I have a sample mean of 4.49. My sample standard deviation is 0.26. And my sample size is 40. And let's just check to make sure that I didn't screw anything up here. Yeah, that looks good. Okay. And we had a 95% confidence level. One thing you want to be careful about is don't just click the confidence level, option and then hit compute. Make sure you have the right value. Usually it's 95%, but again, it could be 90%, 98%, 99%. Okay. And we hit compute. And as advertised, that's what we get. Okay. Notice it doesn't give you the critical value. It gives you the standard error. This is S divided by the square root of N. Okay. It doesn't even give you the sample standard deviation, which is kind of interesting, and it doesn't give you the sample size. So it leaves out a lot of information, even though you entered it and you already know it. It does leave out some stuff that would be kind of nice. Okay. And sure enough, we get exactly those values that we have here on the PowerPoint. So again, we say that we're 95% confident that the true value for the average gas price in that area is between $4.07 and $4.57. Okay, so now you know how to compute confidence intervals for the homework, okay? There's one last thing we want to get a handle on, and we're going to come back to this next week. So this is a good thing to really focus on, and next week we're going to use the results in the next section in a lot more depth. We want to take a look at this margin of error. Notice that the margin of error is where it's at. The sample mean you just compute from a sample. There's nothing there. It is what it is. You get a sample, you compute the sample mean. What makes the confidence interval is the margin of error. That's the key player. And so what I want to do is I want to go back and I want to redo this problem, but I want to change the confidence level from 95% in the previous problem to 90%. So we found out this was the confidence interval when we had a 95% confidence level. And now let's change the confidence level. So I'm going to go to StatCrunch. All you have to do is hit edit. It's really cool. And change this to a 0. And now I'm going to get a different set of values, right? It doesn't let me copy it easily. But if I go to the PowerPoint, and I've already put these values in the PowerPoint, what we see is that the new confidence interval is $4.42 and $4.56 for the 90% confidence interval. Notice that the margin of error here is 25 cents. Okay, the upper value minus the lower value is 50 cents divided by 2 is 25 cents. Here, the margin of error is 7 cents, right? 56 cents minus 42 cents is 14 cents divided by 2 is 7 cents. So what we see is as the confidence level increases, the margin of error increases. Sometimes what people say, and this is somewhat true, but it doesn't give you a good explanation. If you want to be more confident that you contain the true value of the parameter, you have to make the interval larger. So here, notice I want to be more confident that my interval contains the value of mu. So what did I do? I made it larger. Notice the lower value goes lower and the upper limit endpoint is also higher. Okay. Now the reason why, if you go back and you look at the formula, we can understand why that is, right? As the confidence level increases, the area in the middle increases, and what happens is those scores that bracket the area that contains the confidence level gets moved out. The Z or the T score gets larger. So as the critical value gets larger, this is what's actually going on. The confidence level's controlling the critical value, right? If you go up to here, right? This is the confidence level. Okay, as the confidence level increases, those critical values, which are the brackets for that confidence level, they get moved out. And so now you're multiplying by more standard deviations. Remember how we said the standard deviation is like a unit of measurement? This is exactly what you're seeing. Notice that we're describing the margin of error in units of standard deviation. And the T or the Z scores, which is a critical value, is just telling us how many standard deviations. So again, as confidence increases, the area inside increases, the critical values get pushed out, and they tell us how many standard deviations. And so the margin of error also increases. Okay. And that's the better explanation for why the margin of error increases as the confidence level increases. And of course, the confidence interval becomes wider, right? Now we want to see how the sample size affects the confidence interval. So let's rerun the same problem that we just did a second ago. We'll do a 90% confidence interval, but now instead of 40 gas stations, I'm going to make my sample size 80. And we know already from our last problem that this was our confidence interval when we had a 90% confidence level, and our margin of error was 7 cents. I have 70 cents. Let me change that. And now we want to go into StatCrunch and we want to change the sample size. So all I'm going to do is change 40 to 80, sorry. And so you should get 4.44 for the lower limit and 4.54 for the upper limit. And so we see now if we look at this margin of error, it's gone down. Okay. Okay. Notice that the lower endpoint moved up and the upper endpoint moved down. And so the margin of error decreases. And again, we can understand this by going back to the formula for the margin of error. As the sample size increases, notice that the standard deviation of the sample mean decreases. And so you're multiplying by the same number of standard deviations, but the standard deviation of X bar gets smaller as the sample size gets larger. And that's what's going on. So it's good to know what happens. As sample size increases, margin of error decreases. As confidence increases, margin of error goes the opposite direction, and it increases. Okay, so now you have all the information you need to do the homework problems. These are good slides to go back to. This is a good PowerPoint to maybe summarize and make sure that you understand the key points. Okay, thank you.